Hello everyone. In a series of acid-base chemistry, our today's subtopic of lecture is donor number and acceptor number. So before understanding donor number and acceptor number, we have to have some knowledge, some basic knowledge about free energy of solvation. Okay, when acids and bases they are dissolved in some solvent, then they get solvated, and in that process some energy are released, and they have some driving forces also, which is known as their free energy of solvation. So this free energy of solvation is determined by the Born equation, and that equation is also going to be discussed here. First of all, the acidity of a species in a solvent is largely influenced by the solvation of the ions in the solution. Definitely, some acids or base will decompose, so that decomposition will be favored by the role of the solvent. Okay, as much polar the solvent is, the more will be the power of dissociation into some H plus to produce some H plus ions or OH minus ions, etc. Okay, so the acids of acidity of a species, as well as here this basicity can also be said. Okay, so the acidity of a species in a solvent is largely influenced by the solvation of the ions in solution. Next, the Gibbs free energy, that is minus delta Z0, okay, of solvation. So some species are dissolved, so there must be some thermodynamic parameter which is the minus delta Z0. So that will be a function of the radius of the ion, that will be a function of the charge of the ion, and as well as the permittivity of the medium also. Okay, so the parameters are R is the radius of the ion, Ze is the charge of the ion, okay, epsilon R is the permittivity, relative permittivity of the medium, and this is expressed by the Born equation. As I have said, that Born equation is delta G0 equal to minus, this negative sign is here placed in the right hand side of the equation, nz is square, nz square is square by 8 pi epsilon 0 R into 1 minus 1 by epsilon R. Epsilon 0 is the permittivity of vacuum and n is the Avogadro number. Okay, so by the help of this equation, the free energy of solvation can be determined. So it is clear, it is reflected from this equation that as much negative value of the delta G0, there is more active solvation taking place. That means solvation is favored by the negative delta G0 value of interaction of the solvent with the acids or bases. And here some parameter z square by R, it has a special terminology which is known as the electrostatic parameter. Sometimes it is denoted as xi. In some books you will find that the equation is written as n xi e square by 8 pi epsilon 0. The z square by R term is vanishing there, so nothing to worry about that. Here instead of that, xi would be written. In this context, our next features are, it is expected that small ions having higher charge will be highly stabilized in a polar solvent. Definitely, let's have a look on the Born equation here, that the permittivity, relative permittivity of the medium. So if this parameter is increasing, then its reciprocal will be decreasing, then 1 minus its reciprocal will be increasing, and as a result this negative value will be increasing. So higher the ER epsilon R value, then more negative will be the delta Z0 value, isn't it? Okay, so that's here written, larger the value of epsilon R, more will be the negative delta Z0 value, favoring formation of ions in the solution. So it will favor the formation of ions in the solution. That means that it will favor the ionization of the acids or base molecules. Okay, so polar solvents will favor proton transfer leading to charge separation. This is very well known fact to you, because suppose I give you an example of hydrogen chloride gas. Okay, so HCl will not dissociate, will not self-ionized, will not be ionized as H plus and Cl minus until it is dissolved in water. Okay, in presence of water it will become an acid, isn't it? So polar solvents will favor proton transfer leading to charge separation. The conjugate base of A negative of an acid HA will be stabilized in a polar solvent at H2O. Definitely, suppose you have taken as an acid HCl, so its conjugate base would be Cl negative, and that Cl negative would definitely be stabilized by the polar solvent like water. Water has a positive pole and a negative pole as well as, so the positive poles will be headed towards the negative ion, that means the chloride ion. These facts are also applicable to the Lewis acids and Lewis bases. So not only for protonic acids but also for Lewis acids and Lewis bases, these facts will also be applicable. Reactions with an increase in neat charge will be favored in a solvent of high relative permittivity. So if the relative permittivity of the solvent is greater, then there will be some reactions that would happen where the neat increase of the charge will be favored. Our next point in this feature are the common polar solvents are hard Lewis bases, for example water, alcohols and ethers and amines, etc. So hard acids and hard bases theory are not discussed in this series of lecture, okay, but it will be discussed very soon in any of my next class, okay. But for right now I give you an information regarding this, that hard bases actually favor to combine with hard acids and vice versa. That means soft acids like to combine with soft bases. Example, sodium hydroxide is a hard base, okay, whereas the acetate ion is a soft base, okay. OH minus is a hard base, whereas acetate ion is a soft base. That means they are unstable. They are actually always they would like to combine with the cationic charges, whereas OH minus ion would like to exist independently. So that is the hard base. Similar thing also applicable for the cations also, okay. The cations which are actually the ionic atmosphere surrounding it has some hardness, okay, the hard surface, then it is a hard acid, and if it has a soft surface, it is a soft acid, okay. So as much as the cationic charge is higher, it becomes more hard, okay. And the fact is that the hard acids like to combine with hard bases and soft acids like to combine with the soft bases. So very soon we are going to discuss on this topic, but for now you just have this knowledge that water, alcohols, ethers and amines all are hard Lewis bases, okay. And in this context, one more thing, suppose you have some O site, oxygen site, and on the other hand you have some sulfur site. So both has lone pair, both are donors, isn't it? But the oxygen site is harder for its small size, whereas the sulfur site, SITE site, is softer for its actually larger size, okay. So try to imagine what can be a soft thing, what can be a hard thing, okay. Suppose you are given a tennis ball and a football. Tennis ball will be a hard thing, a football will be a soft thing. So this is something like that, okay. Other important basic solvents are DMSO, dimethyl sulfoxide, so CH3 whole twice, SO, DMF, dimethyl formamide, HCO in CH3 whole twice, and acetonitrile, CH3CN, okay. DMSO may also act as a donor through the soft S end, as I have just told you that if you have some sulfur site and sulfur has some lone pair which has some donating tendency, then this site is soft, okay, and it is an ambidentate solvent. That means this solvent can interact via or through its sulfur end as well as its oxygen end. Look at the structure of this. Here there is sulfur double bond O, two methyl groups, then sulfur double bond O. So this sulfur has one lone pair and this oxygen has two lone pairs. So these two lone pairs may also act as a soft base, and the lone pairs of oxygen may act as a hard base. So both sulfur and oxygen can play the role of a donor. So this is an ambidentate solvent. Okay, ambidentate means it can play the role of, it can play a dual role. Dual role means the role of a donor from sulfur site as well as the role of a donor from oxygen site. Next, hydrogen bonding by this part is very important. Hydrogen bonding by a solvent may influence the acidity or basicity of substance. Okay, where there is suppose both the solvents have the similar relative permittivity, but if any one of them has the privilege of formation of hydrogen bonding, has the privilege or the advantage of having the power to form hydrogen bonding, then that would influence more acidity of the acids or more basicity of the basic substance. So what is written here? Hydrogen bonding by a solvent may influence the acidity or basicity of the substance. Thus, HCl, hydrogen chloride, is a stronger acid in methanol than in dimethyl formamide. Why? Very simple. Methanol has an active O bond H site that can form the hydrogen bonding, that has the power to form hydrogen bonding. This hydrogen is has highly positive delta positive value, isn't it? That means delta positive value means it is positively polarized, so it can easily form a hydrogen bonding with the conjugate bases like chloride here. But dimethyl formamide does not have any kind of site like this. Both has similar type of relative permittivity, but methanol would influence more acidity towards the acids. Okay, so what is written here? Thus HCl is a stronger acid in methanol than in dimethyl formamide. In methanol, the chloride ion is stabilized through species like this hydrogen bonding. Okay, so this type of hydrogen bonded species would be formed, but DMF has similar relative permittivity. As I have said, that DMF has almost similar relative permittivity as with methanol, but does not have a hydrogen bond donor center. So this is a part from which you can answer a short question like this. Now move to our main point, which is donor number. Actually, donor number, acceptor number are the characteristics of the solvents. Okay, from with the help of this parameter, donor number or acceptor number, you can characterize a solvent. You can have a comparative study of the solvents in which acids and bases are dissolved, and they are playing the role of an acid as well as a base. The basicity of and this thing, one thing in the initial part I have said the minus delta Z0 value. Here I am going to discuss the delta H value, that means the enthalpy value. Okay, and this enthalpy can easily be calculated with the help of calorimeter. So they have a practical verification, and these are all practically they can practically be determined. Okay, they are not theoretical, they are all from the experimental facts. They are obtained from experimental facts. The basicity of a solvent may be expressed quantitatively in terms of enthalpy of adduct formation. You know the term adduct. Okay, with a reference acid like the strong Lewis acid like antimony pentachloride in 1,2-dichloroethane. Actually, antimony pentachloride should be dissolved in some solvent, and then this will be taken as a reference acid. Okay, now this is some reference acid. Okay, and within this reference acid, with the help of this reference acid, the donor number of the base can be determined from the delta H value, the enthalpy of formation of adduct. So actually antimony pentachloride is the reference, whereas the variable parameters are the solvents here. It's a constant. Antimony pentachloride is a constant. It will not be changed, but the solvents will be time to time changed in order to verify their tendency to donate their lone pairs. Here is the adduct form, antimony pentachloride. When it is dissolved in 1,2-dichloroethane, okay, then it forms an adduct with the base. Base has some lone pair. This adduct is formed. Now, what is the enthalpy? This is determined by the calorimeter. So this delta H0 value, okay, is determined as in the unit kilocalorie per mole. Okay, and this value is actually termed as the donor number. So donor number actually is not a number, it's actually a property, a thermodynamic property. Okay, in kilocalorie per mole, if you can determine the enthalpy change of a reaction of adduct formation, then this is the donor number. So higher the donor number, stronger is the Lewis base. That means the basicity of the solvent. More basic is the solvent, higher would be its donor number. Similarly, another term, acceptor number, this will be applicable for the solvents which are acidic in nature. Okay, so a related parameter called acceptor number, in short AN, of a solvent has also been derived with triethyl phosphine oxide, or C2H5 whole thrice PO. Okay, phosphorus has 5 bonds. In 3 bonds there are C2H5, and in 2 bonds there is double bond O. O has 2 lone pairs. Yes, here one is shown here, but oxygen has 2 lone pairs. Okay, so this lone pair is playing the role of a base, and very much you are aware that these ethyl groups has plus I effect, that is inductive effect, positive inductive effect. For that, these lone pairs becoming very much available. So it is a very strong base. Okay, and this is taken as a reference base. No solvent is required here, like SbCl5. Like SbCl5 was dissolved in 1,2-trimethyl but here it is not required here. Okay, so this is the reference base, and now the corresponding solvents, within the corresponding solvents, this reference base is dissolved. Okay, and similarly the donor acceptor interaction takes place, and from that the delta H value is determined, and that one also expressed in kilocalorie per mole, and that is the acceptor number. Numerical values of the acceptor number are derived arbitrarily by setting the scale to 100 for the base in SbCl5 and 0 for the base in hexane. Now how are the values set? Okay, now the base is antimony pentachloride. Okay, so in antimony pentachloride, okay, if it is whatever be its value, it is set as 100. Suppose it is 540 kilocalorie, so 540 is taken to be 100, and suppose it is 100 in case of hexane. Okay, so 100 is taken as 0. So 100 to 540, that means this 440 value is the overall scale. So 40 each 4.4 kilocalorie per mole value is taken to be 1 unit. So if the delta H value in some other solvent is suppose 104.4, then its donor number is 1. And if it is arbitrarily, this 540 and 100 is arbitrary value, and if it is 536.6, 4.4 minus 535.6, then its donor number is 99. Okay, so higher the acceptor number, strong is the Lewis acid. Very simple. Now I give you a tabular data. Okay, some donor number, acceptor number, and relative permittivity at room temperature of some solvents. So keep it in your mind that these are the characteristics of the solvents. Donor number, that means the tendency to donate their lone pair. Acceptor number, the tendency to accept their lone pairs. Okay, and for Lewis acids, this is some parameter which have been determined in the lab. First time practically in the lab. Okay, Lewis acid actually and Lewis base are those acids and bases where there had been no such parameters by which their strength could have been measured, but here with the help of donor number and acceptor number, their comparative strengths can be measured thermodynamically. And here is the table. So this is the last slide of this lecture. So have a look. Here also relative permittivity of the solvents given. So we find benzene has the lowest and water has the highest relative permittivity. Okay, and find that the acidity of water is 55. Okay, that means it has the delta H value 55 kilocalorie per mole, whereas in case of base, or that means when it is reacting with antimony pentachloride, okay, it is releasing 18 kilocalorie per mole of energy. When it is reacting with ET3PO, then it is releasing 55 kilocalorie of energy. So very simple. When in benzene SbCl5 is dissolved, okay, the actually 1,2-dichloromethyl solution of SbCl5 is dissolved in benzene, then it is releasing only 0.1 kilocalorie per mole of energy. When triethyl phosphine oxide is dissolved in benzene, then only 8.2 kilocalorie energy is released. Okay, so this way we can comparatively study the relative acidity and basicity of the solvents. Solvents play a vital role in the acidity and basicity. That is why their study is also very important, as well as for determining the strength of the Lewis acids and Lewis bases. This donor number and acceptor number are also very important. Okay, they are also the similar way. Instead of solvents, the acids and bases are actually allowed to form adduct with the base and reference acid respectively. The reference acid is SbCl5 in 1,2-dichloroethane, and the reference base is triethyl phosphine oxide. Okay, and here you find that the strongest acidic substance is here pyridine. Strongest basic substance is here pyridine, and the least basic substance is benzene here. And here the strongest acidic substance is water, and the least acidic substance is diethyl ether. Okay, so that's all about donor number and acceptor number. That's all for today, and thank you.